Last time in class, we talked about how we had to amend our definition of tangent line. A tangent line has a perfectly good definition if we're talking about a circle. It's a line that crosses the circle only once. But we would like to have some sort of similar notation or similar notion of tangent line for arbitrary curves. So what we did is we considered an arbitrary curve like the one pictured right here. And we wanted to figure out what would it mean to have a tangent line at this point A. Okay, so here's this point A comma f of A. Let me zoom in real quick. Crucial picture here in the development of the derivative. We have this point A comma f of A, and we want to know like how we can define this tangent right here. And so what we do is we simply scoot away from A by some distance h, and talk about a secant line. So we talk about this point right here, which is f evaluated at a plus h, this extra distance away from a, and the x value a plus h. And let's put a line that goes through these 2 points. Of course, the slope of this blue line would be rise over run. The rise would be this whole distance, f of a plus h, minus the distance f of a, which is simply this distance right here. That's the rise of this, the slope of this line right here. And the run is, of course, this distance h. But that is certainly a bad definition of a tangent line because this secant line right here crosses the point twice. And it doesn't perfectly match sort of the behavior of f of x at the point A. So what we do is we make it a little bit more accurate by simply shrinking this distance h. And we shrink it so much that we, in fact, let h approach 0. We take the limit of the quotient here as h approaches 0. And this sort of point, we want to imagine this point as we do that gliding along this. And notice that this blue line will get more accurate and more accurate and more accurate as I sort of glide this bead along the wire to force it closer and closer and closer to this point A. And soon, after we take the limit, that limiting value will have a slope of this green line right here. This is actually going to be the definition of our tangent line, but let's put it actually in words. This is what we developed in class. So nothing new. We say that the derivative of f at a, f prime of a, is going to be the slope of this green line right here. And how do we find that slope? We have the slope of the secant line right here. So here, let me maybe in blue. This secant line, oh, that's this slope right here. And in green here, this slope of the tangent line is going to be the slope of the secant line, but we've taken the limit. Okay, so it's like the limit of the secant lines. Okay, I kind of just destroyed my work here, but that's really important to see the subtle difference there. And this slope is the derivative. So when we think about the derivative of a function at a point, we really want to think of the slope of the function at that point. Notice perhaps the derivative up here would be a little bit larger because it's a bigger slope, and we have some sort of slope right here, and that is the slope of the green tangent line, and it is this definition, f prime of a, that's how we read this, or the derivative of f at a is equal to the limit as h approaches 0. So this distance that we took away from a shrinks to 0 of the slope of the secant line. In other words, f of a plus h, that's this distance right here, minus f of a, that's this distance right here. So this numerator is going to be this distance, as this illustrates, divided by the run, which is simply this distance right here, also known as a plus h minus a. And that slope makes sense. The slope of the tangent line makes sense as long as this limit exists. Okay, so absolutely huge. Of course, that's mostly notation. Sometimes it's helpful to immediately see why this is useful. So in other words, let's force this independent variable to be something like time, for instance, and force this dependent variable to be something like position, for instance. So let's say we're watching some sort of particle move along a wire or move along sort of like one-dimensional space here, and we notice that it is, I don't know, 1 centimeter 1 centimeter when we start our clock. So here's like 1 centimeter. It doesn't matter the units here, or just one, a distance of 1. When we start our clock, 1 second later, so t is equal to 1 here, the distance is equal to 2. So 1 second into our observation of this particle, the distance away from some sort of arbitrary origin here, our particle literally so far, we see the particle here. Like what this picture is trying to demonstrate is that when we start our clock, we see the particle here, and then the particle moves here, and at 1 second, we see the particle move right here. And then we're into the second, the particle goes like this, and at 2 seconds, we clock so that's what this is right here. We clock the particle at 3 units away from the origin. At 3 seconds, we clock the particle at 2 units away from the origin. And then it looks like, okay, so it crosses 2 units a little bit quickly here. And at 4 seconds, we clock the particle at the ocean or at the origin. So what we should see is at sort of the 0 value of the independent variable, we should see the output. So input would be the t values. So input of 0. The output should be 1. The input of 1, the output should be 2. Okay. The input of 2, the output should be 3. The input of 3, the output should be 2. And the input of 4, the output should be 0. So what would that graph look like? Let's back up. I already made it for us. It should look like this guy right here. So notice again, at the input of 0, so here's my independent variable time and our dependent variable position. The input of 0, the distance away from the origin is 1. That's this right here. So at t equals 0, the distance away from the origin of our particle is 1. That's what we're clocking right here. At 1 second, sorry about that, I pressed the wrong button. At 1 second here, the particle is at position 2. That's what this illustrates. At 2 seconds, we see our particle kind of go past position 3 and then back to position 3, and we clock the particle a distance of 3 units away from the origin at 2 seconds. That's what's going on right here. So 1, 2, 3, right here. And then, of course, right here, we see at 3 seconds, right here, the particle is 2 units away from the origin. And at 4 seconds, the particle crashes to a distance of 0 away from the origin. What if I wanted to know the particle's speed at the exact moment of 1 second? So in other words, to watch this whole thing occur, this particle does this. Right? And we can think about it like this. Again, this is a position versus time graph. It's a rough sketch, so my sketch isn't great. What I want to know is how fast the particle was going as it crosses this point right here, or at 1 second into its motion, how fast was the particle going? What we could do at the beginning is say, well, let's just average the motion from this moment of time, starting our clocks at 1 second and ending our clocks at 2 seconds. And what we would do is we would compute the slope of this blue line right here. And that slope is, by definition, the average velocity of the particle from 1 second to 2 seconds. And it's, by definition, the position of the particle at 2 seconds, so that would be 3, minus the position of the particle at 1 second, which is right here. So that's change in position. And if we notice, the change in position technically in this case is 1 meter. We go from 2 meters to 3 meters, which means that we have the total change in position is 1 meter. Over change in time, so how long that took. Notice that the particle goes from here to here in 1 second. So 1 meter over 1 second, that's 1 meter per second. But that's not very accurate for how fast the particle was going at this moment. So we just measured how long this part took, pretty much. We want to know how fast the particle is going right at this moment. So what we do is we just computed the slope of the secant line. To make it more accurate, we push this bead to go back along the position curve and force it to be right, or we shrink the time interval is really what we're doing. We force it to be right next to this one, and that creates this new thing called a tangent line. And by definition, that tangent line, or the slope of that tangent line, is the instantaneous velocity at 1 second. And that's by definition the limit as h approaches 0 of the position at 1 plus h minus the position at 1 divided by h. And that is the slope of the green tangent line. I have the green tangent line right here. Notice that this green tangent line like perfectly grazes the sort of position curve right here. This is our position curve. That green tangent line, the slope of that line tells us how fast the particle was going, or how quickly the position was changing at that moment in time of 1 second, okay? And this is really the core idea. That is, by definition, by the way, instantaneous velocity. This was Isaac Newton's intention. He wanted to observe how fast particles moved at moments of time rather than over intervals of time. So this is the average velocity, and this is over an interval of time. We want more accuracy. That way we can observe some sort of physical state in a moment and predict the future. Really, the power of physics is predicting the future, and calculus is the lens through which the physicist looks in order to sort of see the future. The slope of this green line is going to be the speed of the particle at a moment of time. So now all of a sudden, the world is revolutionized. We know how to measure speed in a moment of time. Really what we're saying is take that, Zeno, because Zeno says, I don't think motion makes any sense because at any instant, there's the famous arrow puzzle. The arrow is not moving at all. So how does the arrow cover ground if at every instant of time, the arrow is not moving? Because then as we're flowing through time, the arrow is not ever able to move. This fixes that. This instantaneous velocity, this idea of the instantaneous rate of change of position, that's what this is. Also known as instantaneous velocity, also known as the derivative of the position function. This is a derivative. Instantaneous velocity is a derivative. And that's what we're studying. So all of a sudden we can see how quickly something is changing at a moment of time. And at this point I'm rambling, so I'm going to move on. We're going to see how else this is sort of helpful. The big thing here is it's helpful that we have some sort of position function. We can see this position function through observation. And then what we could do is calculate a new function that tells us the speed, the velocity of this particle at any moment of time. In other words, what we can do, what velocity really is the slope of the position function. That's what this is. So we have a less steep slope here, a little bit more steep, more steep, more steep, more steep. Oh, then it levels off. The slope is 0 here, and then it's declining, steep decline here. So what we could do is create a new function that tells us the slope at any of these times. And what we do, how we define that, it's pretty intuitive. For any function f, we denote by f prime, again this reads as f prime, the function whose domain is the set of all numbers x, such that f is differentiable at x, and whose value at x is f prime of x is equal to this limit. So pretty much we can create a new function whose output is this limit. So f prime of 2, say, is simply me replacing this x with 2. And that creates a whole new function. If we collect all x values where this limit exists, then that creates a whole new function that depends on the parent function f. But what this is a slope machine. What this function does is it tells us the slope of the original function f at any x value where the slope is defined. Another way you could say this was mentioned in class, but this definition of the derivative is equivalent to this. And because of our understanding of limits, epsilon deltas, and things like this, we have the tools to understand that these are expressing the same thing. Right? That's not just me telling you that. We can prove that this object is the same as this object through the epsilon delta definition of the limit. Okay, so we over the next 2 months, we're just going to get used to how to deal with this and what it represents. One thing you'll hear me say a billion times, when we think about derivative, We think slope. That's really the core thing I'm trying to emphasize. Of course, when we say derivative, we mean instant, like slope at a moment or a slope at a point. But if we understand that the derivative is really just measuring slope of some sort of other function, then we are really going far in calculus. That is a great understanding of what the derivative is. A derivative is really a machine that tells you the slope of a function at any point, provided that slope exists. So this is huge. I can't emphasize this enough in this class. When you think derivative, you think slope. When you think slope, you think derivative. That is the mark of a calculus student. Okay. Let's see how else we can talk about this derivative. I have a whole lesson here. Okay, here we go. Yeah, and we also have a new definition of a tangent line. This is a great question that kind of motivates how this new definition of a tangent line for arbitrary curves is different than the tangent line for a circle. Notice that the tangent line for a circle is a line that crosses the circle only once. But if we think about tangent line for an arbitrary curve, maybe like a parabola, simply saying that we want the line that crosses the curve only once is not good enough, because two lines do that. There's the perfectly vertical line and the line that actually grazes, oops, pretend that touched, grazes the curve at that point. One of these we want to be the definition of the derivative, and the other we do not. We don't want this vertical line to be the definition of the, the definition of the tangent line. We want this one to be the definition of the tangent line. So notice that there could be two tangent lines in this case, which means that simply saying that a tangent line crosses the curve only once is not good enough, because there are two lines that can do that. But not only could there be two lines that do that, sometimes we have like a tangent line, say we have a sine curve or something like this. We could have a tangent line, say we want the tangent line at this point. Notice it's not at the peak, it's close to the peak. We want the line that kind of grazes the curve right there. So this would be that line, but notice that this line is crossing the curve a few times, even though that really is what we want the tangent line to be. So this is what we want the tangent line to be. It crosses the curve a few times, which means that saying a tangent line is the line that crosses the curve only once is not good enough anymore. And to kind of illustrate that, the new definition, we abandon that definition. We say, no, it's not the case that a tangent line to an arbitrary curve is the line that crosses it only once. The tangent line to a curve at a point is the line that goes through that point and has the derivative as a slope, pretty much. Has this fancy limit as h approaches 0 of f of a plus h minus f of a divided by h as the slope of the line. To illustrate that tangent lines do cross the curve more than once, we have this example. So we're going to show that the tangent line of x cubed at a comma a cubed crosses the graph of f twice. And I really should say that's not true. As long as a does not equal 0. So to get a picture here, we have x cubed as a function, looks something like this. Y equals x cubed. And if we were to grab a here, and here's our tangent line at A, grazes it. This is our tangent line. The slope here, m, slope of the tangent line, is by definition, that's m sub t. Geez, what a fail. Let me try again. M sub t is equal to the limit as h approaches 0 of f of a plus h minus f of a, all divided by h. That's definition of the slope of this line. But notice it's going to cross twice. So we're kind of trying to find what that point is and what this original green point is. Of course, this is the same a right here. And f of x here is, of course, x cubed. So we're going to try to discover the 2 points that this tangent line crosses the original curve. In order to do that, we're just going to compute this limit right here. So let's get into it. first applied sort of derivative example. So here, let me actually use this. Here's my solution. First, find the slope of the tangent line, which is by definition f prime of a. All right, so f prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a, all divided by h. And this is equal to the limit as h approaches 0 of a plus h cubed. That's me simply plugging in a plus h into this function right here. This is our f of x. A plus h cubed minus a cubed, all divided by h. But let me just use the binomial theorem real quick to expand this guy right here. It's not too hard. You just do FOIL twice. It's a little bit annoying, but we can get there fast. This is the limit as h approaches 0 of a cubed plus 3 times a cubed times, oh, sorry, not a cubed, excuse me, a squared times h plus 3 times a times h squared plus h cubed minus a cubed. Okay, so fact check me. Use the distributive property twice and show that this object is the same as this object. But now we see some nice simplifications. This is the same thing as the limit as h approaches 0. Notice the a cubes cancel. We got 3 times a squared times h plus 3 times a h squared plus h cubed, all divided by h, but we're lucky. Look, each of these guys have an h, so we can undistribute it, factor it out, if you will. H times 3a squared plus 3ah plus h squared, all divided by h. H's cancel. H approaches 0, and we have this final limit as 3 times a squared. Okay, so we have the slope of the tangent line. So that is 3a squared is our slope. So I'll write that. Therefore, the slope of the tangent line is 3 times a squared. Going back to our picture, we now know that this is equal to 3 times a squared, the slope of this green line right here. If you have a slope and a point, we know this point lives on the tangent line. That is going to be the point a comma a cubed. You can find an equation of the line. So we have 3 times a squared as the slope, and we know that our x naught comma y naught is equal to a comma a cubed, and that's the point that we know exists on our line, so we can use the point slope formula. Y minus y naught is equal to m sub t times x minus x naught. You can just plug things in. We got y minus a cubed is equal to 3a squared times x minus a. Expanding things out, we got y is equal to 3a squared x minus 3a cubed plus a cubed. That tells me that the tangent line, so this is that green tangent line, we're about to figure it out, that's 3a squared x, it looks like we got minus 2a cubed. Okay, so our tangent line is this. Here's our tangent line. We just discovered it. This is the slope-intercept form of our tangent line, and that is y is equal to 3a squared x minus 2a cubed. Slope-intercept of negative 2a cubed, slope of 3a squared. Now, we are wondering, where does this cross y equals x cubed? Well, that's easy enough. We know they both have at least one point in common, and that is the point a comma a cubed, but we want to know what other point they have in common. And that's going to be the blue one in that picture here. So this is just basic algebra at this point. What we do is we set the curves equal to each other. We assume that the outputs are equal, and try to discover what inputs cause the outputs to be equal. And we do that like this. We set y equal to y. So that's going to be x cubed is equal to 3a squared times x minus 2a cubed. And remember, we're solving for x. So in order to do that, what I'm going to do is bring everything to one side. And the key insight here is we already have a solution. So this is the cubic polynomial that carries all three solutions. Well, one of them has multiplicity, spoiler. That carries the solutions of where, or carries the x values of where this curve crosses this line. But we know we already have one solution, and that's x equals a. So how do we figure out the remaining polynomial? Well, we can just do some quick division. So let me do some division real quick to figure out a way to rewrite this cubic. We know that x minus a is a factor. And that's the factor theorem. Okay, so long division. This is not the way to do it. X cubed minus 3a squared times x plus 2a cubed. So we have x times what is equal to x cubed. That's x squared. And we have, grabbing this x squared, distributing it through these guys, we have x cubed. Oh, excuse me. X cubed, and then we have minus a x squared. Yeah, okay, brutal. These are not like terms, so when I subtract downwards, this is going to carry along. These guys will cancel, though, so x cubeds cancel. And what I have is a x squared, and then this drops down, minus 3a squared x. Question is, x times what is equal to ax squared? That's the same thing as plus ax, I think. Bring this guy down. So ax times x, again, polynomial long division. Ax times x is equal to ax squared. Ax times negative a, that's negative a squared x. Adding these guys down, that's going to be, these guys cancel. We got negative 2a squared x. And then bring this guy down. That's plus 2a cubed. X times what is equal to negative 2a squared. That's going to be minus 2a squared. And let's see if this works. Yeah, things are going to work out well. We just showed that x minus a is a factor. And this is going to be the polynomial that remains. And, oh, I think we can factor that one. That's easy peasy. All right, so this is, of course, negative 2a squared x plus 2a cubed. Those guys cancel to 0. And therefore, we can rewrite this polynomial as x minus a times x squared plus ax minus 2a squared is equal to 0. And it looks like we have another. We know that a actually solves this part of the equation. If I just plug a in here, that's going to make this work. Look, a squared plus a squared, replacing x with a, minus 2a squared is 0. So that means x minus a is a factor yet again. And then we simply ask ourselves, well, what would the remaining factor be? I think that would be x plus 2a. Yep, equals 0. And therefore, the two possibilities for x are a or negative 2a. So going back to the original picture, this negative 2a is the x value of this guy right here. So this thing right here, that x value is negative 2a. And this was based on an arbitrary a at the beginning. Notice that we had multiplicity. A had multiplicity 2. And that accounts for this sort of grazing action. This curve hits the line but doesn't go through the line. Since negative 2a did not have multiplicity, our curve goes straight through the line, or rather the line goes straight through the curve. You hopefully kind of remember that idea in algebra 1, or pre-calculus. whatever it was. So what was the original question? Did we answer it? I showed that the tangent line of this guy crosses the graph of f twice. Yes, we just showed it. We showed the two x values where the tangent line crosses the curve once. Notice I had to say as long as a does not equal 0. After all, if a did equal 0, then this would be our tangent line. And notice that tangent line does cross the curve exactly once. So all non-zero a's, if we scoot away from this tangent line, or excuse me, if we scoot away from 0 and create a tangent line, we know that the tangent line will cross the curve exactly twice. That's what we just showed. And a lot of your quiz questions are finding these tangent lines and expressing these tangent lines and stuff like this. So now we have a definition of a tangent line, and this new definition has this as the slope of the tangent line, and of course has a shared point of the curve, but we don't require that tangent lines cross the curve only once. Here's a great example. Our tangent line crosses twice, even though this green line is officially the equation of our tangent line. And it had, here was the equation right here. Like that is the tangent line of this curve at the point a comma a cubed. All right, we got a lot to talk about, so let's keep going. Conceptual question. When is a function not differentiable? Here are 3 examples of functions that are not differentiable. To think about not differentiable functions, we want to think about functions that are pointy or have some sort of point, that are not smooth. Notice here, this looks like maybe some sort of absolute value function. This is like, I don't know, maybe the absolute value of x. Right here, we would not say that this function has a derivative at x equals 0. You might be like, why? Why not? Well, think about the derivative like this. As a slope, how many different slopes occur when x equals 0? Well, if we slightly look to the left, like if I were to zoom in here, if we slightly look to the left here, the slope is clearly going to be negative. All right. But if we just scoot barely to the right of 0, the slope is going to be positive. So we ask ourselves, well, which one is it? And the answer is, well, there is no solution. The limit of this function as h approaches 0, the limit of the tangent line, the limit of the secant line as h approaches 0, the secant line from 0 to h, does not output a single limit value. And we remember, if a limit outputs 2 separate values, then the limit does not exist. And therefore, because of this point right here, we can't come up with what a good slope would be. Is it this positive version or is it this negative version? And therefore, we say that this curve has no derivative at x equals 0. The derivative does not exist. To be more precise, the limit of this, say if this is function f of x, the limit as h approaches 0 from the right of f of, I guess it would be f of 0 minus, or excuse me, let's do, 0 plus h minus f of 0, all divided by h. This would be positive, whereas the limit as h approaches 0 from the left, f of 0 plus h minus f of 0, divided by h is negative. Okay. So that's really crucial. If you ever see a point, if your function is pointy, like in this case as well, we have this curve right here, even though it kind of almost makes up for it, the slope is still negative on the left side of 0 and then positive all of a sudden on the right side of 0. That's not differentiable at x equals 0. You can't come up with a good slope here. Same thing here. We got a negative slope on the left side of 0, positive slope on the right side of 0. So who's going to decide? Is it the negative version or the positive version? The answer is nobody. This limit does not exist. And then things can get chaotic. Notice that this curve is continuous. This curve is continuous. This curve is continuous. And this disastrous curve, which is pointy everywhere, is continuous. But none of these guys are differentiable at 0. So just because you're continuous does not mean you're differentiable. But it is definitely the case that if you are differentiable, then you are continuous. That was proven in class. So the big idea here is this. when we think derivative, this has already been mentioned, but I can't emphasize this enough. When we think about derivative, we want to think about slope. When we think about differentiable, so this word right here, we want to think about the word smooth. Okay? That is so huge. This box, really, really important. Understanding the derivative, that's really... so this is a noun, and this is an adjective. So the noun version of the derivative really is associated with the noun slope. Differentiable is an adjective of a curve, and when we say a curve is differentiable, we really mean that the curve is smooth. If the curve is not smooth, then it's not differentiable. Okay, so maybe I'll even write that. That was good. This is a noun. The derivative is a noun. This is an adjective. So if somebody asks, hey, is this curve differentiable? That's like a fancy calculus way of saying, hey, is that curve smooth? Really, really important. Notice that none of these curves are smooth. Pointy, pointy, pointy. Even if it's just a slight point, like in this case, we still can't call it differentiable. And of course, this one's a disaster, not even sort of smooth at all. Okay, so when somebody says a function is differentiable, we think to ourselves, oh, they're asking, is the function smooth? That's really a key insight with this new beast of differentiable. Yeah, so that's absolutely huge. And understanding the derivative is simply a fancy way to say slope. Okay, a little bit of a break to talk about notation. If we have a curve y, and we call that curve f of x, each of these objects mean the same thing. I think people call this Newtonian definition, this f prime of x. This is the one, we read this as f prime of x. Let me write that down. F prime of x. That's how we would read that. We would simply read this as y prime. We simply read this one as dy dx. So that's like a phonetic pronunciation. And this is the derivative with respect to x of f of x. So derivative with respect to x of f of x. All of these objects mean the same thing. I think people call this Newton's notation, but Newton didn't really use that. Newton used these, like, if he wanted to talk about velocity, which we were talking about, which is the derivative of position, he used these dots, which is kind of cool. I wish we didn't abandon those. And this would be acceleration. So this is acceleration. This would be velocity. And this would be position. That's how Newton got his ideas out. This is what he called the fluxion of position. It's also kind of cool. I like Newton's words, but we sided with Leibniz as humanity, which is fine. This notation means the same as this notation, which means the same as this notation, which means the same as this notation. The plight of learning a new language here, all of you guys learning the language of calculus, is we have different words for the same thing, and that's what we're learning about here. We will use these interchangeably. Sometimes maybe one example, this notation fits the best, where another example, this notation fits the best. And it's a good skill to kind of ask yourself how you would go back and forth between these and express the same idea. But just be on the lookout that these objects mean the same thing. This one is a little bit more, I think this one might be the mathematician's favorite. I like this one the most, but this one might be a mathematician's favorite because it illustrates what's moving. So this is how the output or the dependent variable changes as the independent variable changes. dy, change in y, divided by change in x. So notice I just said divided by, but here's a big old alert. We got to be aware of this. This is not a fraction. Indeed, that is not a fraction. We can't treat dy is not a number. It's more of an idea than anything. When we get a little further in this class, we will have an official definition. dy can be treated like a function. If you want to see the official definition, that's fine. This is what dy is. dy is literally a function. So anyways, not a fraction. We can't treat it like a fraction. Be very careful. And this is kind of funny, but because there's going to be results, like soon we're going to learn about the chain rule, and then we're going to see that there's an expression for this thing that makes it look even more like a fraction. But just be careful. This object in the numerator of this notation, that is not a number. We can't always treat it like a number. These are more like ideas. This is x changing to, or the difference in x changing to 0. And this is like difference in outputs going to 0. So just be cautious. Even though it looks like a fraction, this is notation, not a new mathematical object. This is a notational way to say the derivative of y with respect to x. Okay, the derivative of f with respect to x. Notice that what it kind of looks like happened is this y was substituted with f of x to go from here to here. Kind of like that here. F of x was substituted with y to go from here to here. So there's kind of like, clarity in notation in that sense. Be used to all of these. Know that all of these mean the same thing, and that is the derivative, the slope of the function f at a singular point. All of these are functions, also important to mention. Notice that x is not a particular value necessarily, but this is a function that collects the slope of the original curve f of x, y equals f of x. All right, big thing to mention. This is kind of just making sure we're touching base on enough things. All right, good example right here. We are going to show that this function here does not have a derivative. In other words, is not differentiable at 0. It doesn't make sense to talk about the slope of this function at 0, where this function does have a slope that we can talk about at 0. To kind of convince ourselves of this, I'll do like a quick sketch of what these functions look like. This function looks like this. Quick sketch. Oh, I can't do that. Hold on. It goes like this, and then it shrinks like this. But these two lines here, these lines have slope of 1 and -1. Notice at 0, how are you going to talk about the slope of this function? In a similar way, the absolute value does not have a slope. But let's actually show that. Let's show that this function is not differentiable at x equals 0. In order to do that, we're just going to compute f prime of 0. So here's my solution. Let's just go by definition. Here's my solution. Let's see. By definition, f prime of 0 is equal to the limit as h approaches 0 of f of 0 plus h. Again, this is definition. Minus f of 0, all divided by h. But let's check this out. This is equal to, well, let's figure out what this numerator is. This is f of 0 plus h. That's clearly just f of h. So this is the limit as h approaches 0 of f of h minus f of 0. And in order to do that, we have to ask ourselves, okay, so we're putting some sort of input. Which one of these parts of the function do we want to look at? The input is equal to 0, so this is the part of the function we want to look at. This is how the function is defined when the input is 0. That's what this says. So I can replace this f of 0 with, well, 0. Let's do it. All divided by h. And then we ask ourselves, what is f of h? Well, h is approaching 0. H is not equal to 0. That's the definition of this limit. So I ask myself, which part of the function do I look at? It's this one up here, because h does not equal 0. And therefore, this part of my function is what I should input there. This is equal to the limit as h approaches 0 So that was h times the sine of 1 over h divided by h, and hopefully we are seeing the issue here. This is equal to the limit as h approaches 0 of the sine of 1 over h, and this limit horribly does not exist. To illustrate why this does not exist, we would be taking the sine of infinity in one direction and the sine of negative infinity in the other direction on both sides of 0. And sine itself never calms down. So sine's going to look like this. It's never going to settle into a limit. As h approaches 0 from the left, we have the sine pretty much of infinity, but the sine never settles down to some sort of limit value. Any epsilon cannot be met with a delta. Okay. Therefore, the limit does not exist. This derivative does not exist, and we would say, therefore, f is not differentiable at 0, at x equals 0. But let's look at this other function, g of x. Let's see what happens here. G prime of 0, that is going to equal the limit. Notice the only difference is we have an extra x out front. So it's almost like we multiplied f of x by an extra x to create this new function, g of x. We have the limit as h approaches 0 of g of 0 plus h minus g of 0 divided by h. That's the same thing as the limit as h approaches 0. Through the same logic, that's going to be h squared times sine of 1 over h minus g of 0. But to understand what g of 0 is, I can't plug 0 into this part of the function. But luckily, g is defined as 0 when x is equal to 0. So minus 0, all divided by h. Let's check this out. We have the limit as h approaches 0 of h squared times sine of 1 over h, all divided by h. One of the h's cancel, and we have to think about this limit right here. So we have the limit as h approaches 0 of h times sine of 1 over h. That's going to be different because let's remember something about sine. Here's a little bit of a side quest. Sine of anything you darn well please is going to be less than or equal to 1, but it's also going to be bigger than or equal to negative 1. Just think about what sine represents on the unit circle. What happens as I multiply through this inequality by maybe h, I would have negative h is less than or equal to h times sine of star. I don't care what star is, which is less than h. But then I can let h approach 0. This side of the function would go to 0 is less than or equal to the limit as h approaches 0 of h times sine of star, which is less than or equal to 0. So again, I took this to 0 and this to 0, and therefore, by squeeze theorem, remember that guy, super powerful theorem in calculus, we proved it in this class, this limit is equal to 0. Where am I at? Right here. This limit right here must be equal to 0. All right. And that's perfectly well defined. So if this thing right here, g prime of 0 exists, which we just showed it does, that means that g is differentiable at 0, and we have accomplished the task that we were set out to do. Oops. So we just showed that, again, we just showed that f of x is not differentiable at 0 because we have the limit of this sine function. Sine never settles down. And then if we just multiply by this extra x right here, we show that this function, g prime of 0, or g, does have a derivative of 0, and that derivative is 0. Powerful. Okay, Okay, now we're kind of just, again, we're bookkeeping here. What we're going to do is take the derivative of a few famous functions. We're on the final sprint here. It's a bit of a heavy video. We talk a lot about a lot of theory, but we're going to develop a few things that are going to be helpful to us. We want to find the derivative of f at x. So the function f prime of x, we're looking for a function right here. We want to create a machine that tells us the slope of this square root function at any x value. Okay, let's do that. Here's my solution. It's just the definition, you guys. And we're going to notice that it's sort of something we've seen before. I'm going to use the other definition of the derivative. By definition, I think f prime of x is actually equal to the limit as z approaches 0 of f of z, I messed up. Not z approaches 0, z approaches x. F of z minus f of x, all divided by z minus x. Perfectly valid definition of the derivative. But now we're just keeping track of things. That's the limit as z approaches x of the square root of z by definition of f minus the square root of x, all divided by z minus x. But I don't know, you guys. My favorite way to say z is the square root of z squared. Or excuse me, actually, square root of z squared. No, that was right. Square root of z squared. Square root of x squared. Oh, look, I just forced a difference of squares. This is the same thing as the limit as z approaches x of the square root of z minus the square root of x, all divided by the square root of z plus the square root of x times the square root of z minus the square root of x. Oh, nice. Those guys cancels. And those were the problem childs. So now we have the limit as z approaches x of 1 divided by the square root of z plus the square root of x. And this is equal to 1 divided by square root of x plus the square root of x. The thing that's moving is z, and z gets replaced with x. So this thing's going to get replaced with x. And that, of course, gives me 1 divided by 2 root x. So, famous derivative that we need to know for sure. The derivative of the square root of x is equal to 1 divided by 2 root x. And we just showed that to be true. If you're in this class, that is something we got to know by heart. We just got to recognize the square root of x, the derivative of the square root of x, as 1 over 2 root x. To emphasize, what is the slope of the curve y equals root x when maybe x equals 25? This tool tells us exactly what the answer is. We know the slope is equal to 1 over 2 root 25. You just grab that x value, plug it into your slope machine. This is the same thing as 1 over 2 times 5, which is the same thing as 1/10. All right, so now I know this machine tells us the slope of the original curve. Here's the original curve, looks something like this. That's y equals root x. Let's walk to 25. So here's x equals 25. We look up. We go, what is the slope here? What is the slope here? We now have a tool that tells us exactly the slope there, m is equal to 1/10. That's really, really powerful. Wildly powerful. The applications are endless, as we saw in the history video. One thing I wanted to also kind of quickly point out here is the domain of the original function was all non-negative real numbers. Notice that the square root can only take non-negative numbers, whereas the domain of f prime is equal to all non-negative numbers, but we also, in this case, have to make sure x is not 0. So this derivative operation, quote unquote, shrank our domain. Just because we're taking the derivative does not mean the domain of the new function created is going to be the same. Notice our domain shrank. Very often, the domain of f is going to be, well, the domain of f prime can never be bigger than the domain of the original function. Often the domain of f prime is smaller and sometimes drastically smaller than the domain of the original function. This one's just slightly smaller. We just lost 1 point, but that's important to remember, especially if you want to go further in math. Okay, well, I just kind of crowded up my next example. But our next goal is to find the derivative of a famous trig function, and that is sine of x. So maybe I'll go up this time. And we really want, in this next example, I want to, for the rest of this video, really, we want to collect as many trig derivatives as we can. I'll show you how to do one of them, and then taking the derivative of cosine, which will be next, is going to be your homework, but the method is the same. You have to remember your trig identities. Or you can wait until we prove the chain rule, and there's a slick way you can prove the derivative of cosine if you have the chain rule. And maybe we'll talk about that when we get to the chain rule. And then we have to take the derivative of tangent, which really is a quotient, and we need something called the quotient rule. I'm getting ahead of myself. Let's figure out the derivative of sine. Let's go up this time. Let g of x equals sine x. Then g prime of x is equal to, by definition, the limit as h approaches 0 of the sine of x plus h minus the sine of x, all divided by h. Oh, shoot, we know trig. This has another name. That is equal to the limit as h approaches 0 of the sine of x times the cosine of h plus the sine of h times the cosine of x minus sine of x. So again, this part right here, this part is sine of x plus h. Those are the same thing. Okay, divided by h, can't forget that. We have the limit as h approaches 0. To kind of bunch these up, I'll do it like this. We have the sine of x times the cosine of h minus the sine of x. And I'll do plus the sine of h times the cosine of x, all divided by h. So let's check this out. I'm seeing a common factor here. We have this common factor of sine x is in both of these things. So I'm going to undistribute it, factor it out. This is the same thing as the limit as h approaches 0 of the sine of x times the cosine of h minus 1 plus the sine of h times the cosine of x, all divided by h. This is all inside the limit, too. That's important to remember. This is the same thing. Oh, shoot. I'm running out of room. This is the same thing as the limit as h approaches 0 of, how about this, sine of x times the fraction cosine of h minus 1 divided by h plus sine of h divided by h times the cosine of x. And of course, the limit of a sum is the sum of limits. The limit of a product is the product of limits. What we have is the limit as h approaches 0 of the sine of x times the limit as h approaches 0 of the cosine of h minus 1 divided by h plus the limit as h approaches 0 of the sine of h divided by h. Oh, that's nice. We know that limit. Times the limit as h approaches 0 of the cosine of x. Let's take these one by one. This guy right here, the limit as h approaches 0 of sine of x. Well, sine of x has nothing to do with h. this is going to stay sine of x. So let's write that down. This equals sine x. This limit right here, famous limit we've evaluated in class many times, that's 0. Also a famous limit coming up right here. Famous limit, we use squeeze theorem argument and the area of some triangles. That's 1. And last but not least, we have the limit as h approaches 0 of the cosine of x. But the cosine of x has nothing to do with h. So the cosine of x is going to, well, stay the cosine of x as h does whatever the heck it wants. And we have the cosine of x. Giving me a final answer. This is absolutely nuts. The derivative of sine is the cosine of x. Wow, this whole time that you guys were looking at the sine of x, you didn't realize that the close companion, so we have the original curve sine of x, the close companion cosine of x was actually telling you the slope of the original function the whole time. Indeed, if g of x is equal to sine of x, the cosine of x is the machine that tells you the slope of sine of x at any x value. To convince you of this, let's draw a sine curve, just a quick sketch of a sine curve. Looks something like this. So we got 2 pi, of course, we've all seen this before, pi 0. G of x equals sine x. And then let's draw this other machine that we just discovered. Cosine looks something like this. So here we got pi. Here we got 2 pi. This is cosine of x, h of x maybe. So let's look piece by piece. Right here at x equals 0, we're wondering what the slope is of sine of x. So I don't know what that is. It's definitely positive though. It's maybe like 2 or 3, I don't know. Oh shoot, cosine of x tells me that it's exactly 1. So we know that the slope right here of the original sine function is 1. All right, the rise over run, quote unquote, of the sine function, and of course the sine function continues in this way, same with the cosine function, is exactly 1. Then let's go to pi halves. What is the slope right here? Well, it's 0, clearly. Oh, shoot, the cosine has been telling us that all along. Look at the height of this function. It's 0 at pi halves. Crazy. The slope of the sine function apparently at pi is equal to -1. So let's look. Oh, look at it right there. Yeah, believable. -1. Cosine's been telling us that this whole time. Absolutely crazy. I don't know, I get pretty psyched out here. We got 3 pi halves. Apparently, the slope of the sine function at 3 pi halves is equal to 0. So let's look. Here we got 3 pi halves. We should see that the sine function is pretty darn level. Oh yeah, it is right there. Oh, sorry, this was misleading what I was doing right here. The slope of the cosine function, look, the height of the cosine function tells us the slope of the original function. So yeah, that was bad math. The height right here, the height is 0, which means that the slope of the sine function is 0. The height of this function at 2 pi is 1, which tells me the slope of the original function at 2 pi is 1, and things check out. Well, it's at least believable. Okay, for homework, things we have to know. Using this same method, we have that the derivative, so in a box in your brain, you have to know this stuff. The derivative of sine x is equal to cosine x. The derivative of cosine x, using that same method with the trig functions and everything, is negative sine x. Interesting. Convince yourself of where that negative comes from. And then, of course, we can say that the derivative of negative sine x is equal to the negative derivative of sine x. But this thing right here, we already calculated. It's right here. So we have the negative cosine of x. And look at the cyclic action that's going on. Last but not least, we have the derivative of the negative cosine of x is equal to the negative derivative of cosine of x. But that's the same thing as the negative. Notice that the derivative of cosine of x is given right here. So we have negative sine of x, which is just sine x. And we've looped back to the beginning if we were to keep going. Now, what I just did was I kind of illustrated that you can take derivatives of derivatives. All of these derivatives you should recognize, the big ones being these two. We now need to know in our heart that the derivative of sine of x is the cosine of x. The machine that tells you the slope of sine of x is the cosine of x. The machine that tells you the slope of cosine of x is the negative of sine of x. And these two trig functions have a beautiful relationship. Now, what it does seem like I just did, and indeed I did, is take derivatives of derivatives. And that's kind of like asking, what is the slope of the slope? And indeed, there's notation for that. It is possible for us to take derivatives of derivatives and still have it be a function. After all, the first derivative is a function itself. So that function should have some sort of other function that tells us its slope at any value. And indeed, the derivative of the derivative, f prime prime, so let's check this out, f prime prime is also a thing. And it is denoted by f double prime. So f double prime is how we would read that. And this is the function that tells us the slope of the slope. Pretty nuts. And if we wanted to speak in Leibniz's, I guess, that is kind of like this. We have the derivative of the derivative, and we write that as d squared y over dx squared. Notice it is as if we multiplied fractions, but to emphasize again, this is not a fraction. This is simply notationally convenient to explain. Beyond that, the nth derivative is denoted by f to the power of n, but that n is in parentheses. Notice that if it was just this, like if I were to write this, f to the power of n, that is equal to f of x itself, all raised to the nth power. That does not equal f to the power of n in parentheses, because this is the nth derivative. The nth derivative of x. So those are different things. And here's a fun example. Find the 2026th derivative of sine. We just went through this. So if g of x is equal to that sine of x, what we discovered was that the derivative, the first derivative, was the cosine of x. And then I left it to you as homework to find the second derivative of sine. So we have the second derivative. And in other words, what is the derivative of the derivative? What is the derivative of cosine? It can be shown that that is negative sine. And then we have the third derivative. So let's use this notation. That is going to equal the negative cosine of x, and that's with some derivative laws that we had proven in class. And then notice the beautiful thing that happens. The fourth derivative is equal to sine of x again, which is the same thing as g of x. Okay, interesting. So I think every time we take a derivative, and that is the derivative as a multiple of 4, we are going to cycle back to the original function, all right? So every single fourth derivative, or if we take a derivative and it's a multiple of 4, then we know that that is our original function. So for instance, g to the power of, or the 100th derivative of g is definitely just equal to g of x. Because why? Because 100 is a multiple of 4. Let's see, g to the power of 88. I keep saying to the power of, I shouldn't say that. The 88th derivative of g is also just g of x. All right. So if we wanted to figure out the 226th derivative of sine, what we could do is just backtrack the 226 until it's a multiple of 4. But honestly, I don't know. Let's see. Let's think of a close multiple of 4. I don't know, 2020 is clearly a multiple of 4, which means that 2024, here we go. That's a multiple of 4, and we know that's going to equal g of x. So I think the 2025th derivative, taking the derivative on both sides, that is simply g prime of x. And taking one more derivative, what we're asked for. Oh, by the way, g prime of x is the cosine of x. And taking one more derivative on both sides, that is going to be g double prime of x, the derivative of the derivative, and that is negative sine of x. Answering the question. That's kind of cool. The 226th derivative of sine, here's our answer. Negative sine of x. I could also say this. That's negative g of x. All right, that's cool. So we have this kind of modular action with the derivative. Famous mathematician Leonhard Euler noticed that, and he noticed its relation to a lot of physical phenomenon and found some awesome stuff out. Stay tuned for Calc 2/Calc 3 for when we study this further. Fourier also did a lot of sweet stuff with this, these sines and cosines. Okay, so what I did here is we talked a ton. I kind of picked up a bunch of loose ends. There's one more thing I want to do, one more big thing I want to do for this video. Here's what we've done so far. We've done a lot. These videos are heavy. A lot of knowledge goes on here. All important, all really important. It's hard to, I don't know, calculus is so expansive. It's quite a daunting task to really say everything you want to say. But let's take a little bit of a breather. I wanted to emphasize the stuff that we have already proven in class. This first famous result, first of all, we finally defined the derivative. That's what this thing is, the derivative. We want to think about it as a slope machine of the original function. We showed in class that if you are differentiable, then you're definitely continuous. But just because you're continuous, you don't have to be, it's not necessarily the case that you're differentiable. We talked about that today. We talked about the power rule for the natural numbers. We proved that in class. We now know that if y is equal to x to the power of 12, then y prime is definitely 12 times x to the 11th. We showed that in class, proven. That's really powerful. We now have a machine that tells us the derivative of these different powers. And we also proved this right here. If you have y is equal to some number, pi to the power of root 2 or something, that means y prime is equal to 0. All right, the slope of a number, of a constant function, is going to be 0 at all times. That was proven in class. We also have this idea that if you have a number times a function, so like say this example again, if we have y is equal to 5 times x to the 12th power, then what you do is you pretty much just bring this number along as you take the derivative of this part. So I'll say that again. You bring this number along as you take the derivative of this part and do some multiplying at the end. So this is going to equal 60x to the 11th. So that's 5 times 12 times x to the 11th. We proved the sum rule. And the big thing we did is we proved this product rule for derivatives. What I want to do right now is prove the quotient rule for derivatives and then use the quotient rule to expand the power rule for the natural numbers. And let's take it to the power rule for the integers. Remember, the natural numbers are a subset of the integers. The natural numbers are all positive whole numbers. The integers include 0 and all negatives. Turns out this power rule, so powerful that it also works for the integers. And we can prove it once we prove this quotient rule. So let's do it. The quotient rule. If f and g are differentiable and g is not equivalently 0, then the derivative of the quotient of f and g, is equal to this mad crazy expression. All right, let's see how this goes down. Proof. Let's assume f and g are differentiable. And we're also assuming that g is not equivalently 0. Then what the heck object must this be? Well, that's going to be the limit as h approaches 0 of f divided by g of x plus h minus f of x. Whoa, that's wrong. Let me try again. Minus f divided by g of x, all divided by h. All right, that's by definition of the derivative. Oh, but that's the same thing as the limit as h approaches 0 of f of x plus h divided by g of x plus h minus f of x divided by g of x, all divided by h. That is actually the definition of just what the quotient function is. So going from here to here, that is definition of what this object is. So yet another definition. Oh, but I see the difference of two fractions in my numerator, so that's going to be the limit as, let's combine fractions, as h approaches 0 of, okay, so check my work here, but that's going to be g of x times f of x plus h minus g of x plus h times f of x, all divided by h times g of x plus h times g of x. All right, so this is just because fractions. We know how to deal with fractions. That's kind of a little bit hand wavy, but we just added fractions and we divided fractions. We know how to deal with those. I can show more details if needed. And then I'm going to think to myself, hey, this thing right here, f of x plus h, it'd be really nice if I can have a minus f of x added to that. That would be really nice because I know how to deal with that beast. I know that f is differentiable, so I'm going to think to myself, a minus f of x would be really nice to show up here. So what we do as mathematicians is we just force that to happen. Like this. I'm also going to use the commutative property because I'm seeing the future and I want those to line up differently. So we have f of x plus h, and I'm going to immediately take away f of x. So this green step right here, but that's clearly not allowed. So I'm going to immediately add f of x. Then I still have this times g of x. And then I have minus g of x plus h times f of x. All divided by, we have h times g of x plus h times g of x. All right, let's maybe do some distributive property right here. So this g of x is going to distribute to the f of x, and it's also going to distribute to this thing right here. So let's see what we'd come up with. This thing in parentheses. I'm going to put this in parentheses right here because we want that. Those two pieces belong together because we know what the derivative looks like, and that's in my brain. So I want to see an f of x plus h minus f of x, and I want that to tag along. So this is the limit as h approaches 0. In parentheses, f of x plus h, minus f of x, close parentheses, times g of x, plus f of x times g of x. And then what I have is minus g of x plus h times f of x. And this is all divided by this h times g of x plus h times g of x. All right. And then I look at these two guys. This thing right here and this thing right here, and what I'm noticing is common is a negative f of x. So watch this carefully. Make sure I'm not making any sort of algebraic blunders, but I do think this is the same thing as the limit as h approaches 0 of f of x plus h minus f of x times g of x. And like I said, I'm going to factor out a negative f of x In order to do that, I would have a negative f of x right here. But when I distribute it, it has to make sense. So in order for that to make sense, what I'm going to write is a g of x plus h minus g of x. Notice you can simply check my work. So to look at this numerator, when I distribute the negative f of x to this guy, I would have a negative g of x plus h times f of x. Oh, sweet. That's what I have right here. Distributing this negative f of x to this guy, that would be 2 negatives, which makes a positive f of x times g of x. Oh, sweet. That's what I have right here. All right. Really, really powerful. Let's see. Yeah, okay, so in my denominator, better account for that. I'm actually really happy about this because look, long lost friends, g of x plus h minus g of x. I know the derivative of g exists, so it looks like that just magically came into play. Wow. All right, so let's deal with some fractions. I think this is the same thing as the limit as h approaches 0 of... I'm going to divide, let's see, best way to do this. Or best way to explain this, rather. We are dividing h. H is being divided into a difference, all right? We can sort of choose which one of these things in the product we divide h into. We don't divide h into both of the things in this product. We do divide h into this whole thing and to this whole thing, but... at the end of it all, this is really what it's going to look like. Here, I'll just go ahead and write. I'm going to intentionally write fractions inside of fractions. This thing really wants to be divided by h, for sure. So let's see where we're at. Okay, again, I divided this h into this thing and into this thing. Why? Because h and this thing certainly get along. Because now what I can do, I have the limit of a quotient is the quotient of limits. The limit of a difference is the difference of limits. And the limit of a product is the product of limits. Those are all proven in the prior, in like week 1 or week 2. Okay, so this is about to be a mess, but we're almost done. Therefore, we have the limit as h approaches 0. Oh, I actually wanted to distribute that. Let me try that again. Distributing this limit everywhere, what we have is the limit as h approaches 0 of f of x plus h minus f of x divided by h times the limit as h approaches 0 of g of x minus the limit as h approaches 0 of f of x times the limit as h approaches 0 of g of x plus h minus g of x, all divided by h. Oh my gosh, you guys, this is powerful. All divided by the limit as h approaches 0 of g of x plus h times the limit as h approaches 0 of g of x. All right, let's talk about these one by one. This thing right here, famous name, that's f prime of x. This thing right here, g of x, isn't going to change as h does whatever the heck it wants. This is just g of x. This thing right here, again, f of x is not going to change as h does whatever it wants. This is just f of x. Famous name for this thing right here. That is the derivative of g at x, okay? The derivative of g. This thing right here, subtlety. G is differentiable, so it's continuous. I can replace or swap the order with g and the limit. Pass the limit through g and send h to 0. Since g is since g is differentiable, it's continuous, and this is simply going to be g of x plus 0, which is g of x. This is the limit as h approaches 0 of g of x. G of x is going to stay g of x as h does whatever the heck it wants. So what we have at the end of it all, this is the same thing as I'll use the commutative property here too. So this limit first. Maybe I should do that. This is f prime of x times g of x. So again, I just swapped this one. That's f prime of x. This thing right here, that's g of x. Minus f of x times g prime of x. All divided by, this is g of x, and so is this one. So that is usually written as g of x squared. And of course, okay, so this is just how it's usually presented. G of x times f prime of x minus f of x times g prime of x, all divided by g of x squared. And that is the quotient rule. So the justification, a big justification I'll mention right here is g is differentiable. Oh, technically this goes down here. So this justification, g is differentiable and therefore continuous. All right. So this is absolutely huge. We now have a quotient rule. We just proved the quotient rule, super powerful. To really emphasize symbolically what we just said, let's see some examples. A divided by B prime, how I like to remember this, is low D high minus high D low. So let me write that down. Low D high, so D high means like the derivative of the high function, minus high, so I didn't change anything to the high function, D low, derivative of the low function, B prime, all divided by low squared. All right. So if I were to have U divided by V prime, that's the same thing as low D high minus high D low, all divided by low squared. Really, really powerful way to think about it. In fact, let's use this right quick. What is the derivative of the tangent of x? Oh, but shoot, that's the derivative of the sine of x, which we proved a second ago, divided by the cosine of x, which was your homework. So this is the same thing as low cosine of x times the derivative of the numerator, tangent of x. What? Sorry. Derivative of the numerator, which is the derivative of sine of x, minus high, which is sine of x, times the derivative of the denominator, which is cosine of x, all divided by the denominator squared. Again, I'm not taking the derivative of the denominator. I'm simply grabbing the denominator and squaring it. But we know what this is. This thing right here, a second ago, we showed that that is the cosine of x. Your homework was to show that the derivative here is the negative sine of x. So what we have is we have the cosine of x times the cosine of x minus sine of x times the negative sine of x, all divided by the cosine of x squared. Okay, so that's the same thing as the cosine squared of x plus the sine squared of x, all divided by the cosine of x squared. And those of you that know your trigonometry, we're jumping up and down because this numerator right here has a famous name. That is the number 1, ladies and gents. So what we have is 1 divided by the cosine of x squared. This is also known as 1 over the cosine of x squared. And that is also known as the secant of x squared, which is, notationally speaking, you can write that as secant squared of x. Those are the same thing by definition. So add that into your bank of derivatives, the bank of slope machines. What we've done in this class so far, in this video, we have that the derivative of root x is equal to 1 over 2 root x. That's got to be remembered for as long as this class. So as long as you live, really. Just remember this stuff. It's important. We have that the derivative of the sine of x is equal to the cosine of x. We got to know that by heart. Easy peasy. The derivative of cosine of x is equal to the negative sine of x. That's got to be REM sleep, easy to remember. You got to do a lot of practice questions to where that's simple. We have the derivative of some function p divided by q. That is equal to the low function times the derivative of the top function minus the top function times the derivative of the low function, all divided by the low function squared. That's the quotient rule. We have to see this shape with mathematical goggles. We have to know how to take that derivative. And using that, we showed that the derivative of tangent x is equal to secant squared of x. That is also something that we have to know by heart. Okay, so here are the development of our calculus journey here. We now have machines that tell us slopes at any x value. We now have a machine, the cosine of x, that tells us the slope of sine of x at any x value, where it makes sense. We have a machine here, 1 over 2 root x, that tells us the slope of the original function root x at any x value, of course, as long as this makes sense. We can find the slope of the quotient of any two differentiable functions with this slope machine. Well, really, this is a machine that makes slope machines. That's pretty powerful. It's a machine-making machine. And then we have another machine here that tells us the slope of the original function tangent of x at any x value where this makes sense. Last thing, crazy video. Oh my gosh, so much going on. We're here now. I had one more thing on the agenda. I wanted to prove that the power rule, using the quotient rule, we can also show that this power rule for z, or this power rule also works for the integers. So just to show what this says, not only do I know that x squared, the derivative of x squared, is equal to 2 times x to the first power, which is of course just 2x, I now know that the derivative of x to the negative 2, well, once we prove it, I will know that the derivative of x to the negative 2, it also works. So I can just bring the negative 2 down, and then I'll have x to the 1 less than negative 2. That is negative 3. And of course, I can expand this. The derivative of x to the negative 5th power, that's going to be negative 5 times x to the negative 6. If u is equal to negative 4 times z to the negative 18. Oh, why did I just make my job hard? That implies that u prime is equal to positive, okay, here I go, 72 times z to the negative 19. All right. I hope I got that right. 18 times 4, guys. I don't know. If L is equal to negative 1/3 times k to the negative 12, that implies that L prime, the derivative of L, is equal to, bring the negative 12 down, multiply it by the negative 1/3. That's going to be positive 4 times k to the negative 13. Remember, the exponent decreases by 1. All right, so this power rule works even for the integers. Let's do a proof sketch because this video is too long. So, proof sketch. I'll do it in gray. Fill in the details since you are a mathematician. If k is less than 0, since k is an integer, that means that k is equal to negative n for some positive whole number n for some. And therefore, f of x would equal x to the k, which is equal to x to the negative n. And therefore, f of x is equal to 1 over x to the n, which means that the derivative, or here, I can write it like this. The derivative of f of x is the derivative of a quotient. Well, you guys, we just did all of this work to show that we can find the derivative of a quotient. So this is going to be the same thing as the bottom function times the derivative of the top function. All right, so low d high. So x to the power of n times the derivative of 1 minus the derivative of the bottom function, x to the power of n, but we know how to do that. We proved the power rule for the natural numbers, okay? That is proven, all right? So we use the derivative of the power rule for the natural numbers within the proof of the derivative of the power rule for the integers, okay? Times 1, so this is low d high minus high d low, all divided by the bottom function squared, so x to the n squared. The derivative of constant is 0, so that's gone. This is equal to, and we have the derivative of x to the n, that's been proven already. That's negative n times x to the n minus 1, and that's, of course, times 1, all divided by x to the n squared, but another way to say that is x to the 2n. Then we just got exponent rules, you guys. This is the same thing as negative n times x to the n minus 1 minus 2n. Oh, shoot, but that's the same thing as negative n, I'll put that in parentheses, times x to the power of n minus 2n, that's negative n minus 1. Oh, but I could use parentheses here as well. We have another name for negative n. That's k. Oh, look. That is the power rule. So if k is even a negative whole number, the power rule works. We know how to find the derivative. We use the quotient rule for the proof of the derivative of the power rule if k is an integer or if the exponent is an integer. Maybe I'll do like one example to cap this off. We can now take the derivative of a function. If our function maybe looks like this, negative 3 times x to the negative 1 plus 4 sine of x, and then I'll do minus 2 times the square root of x. We can find y prime using all this new knowledge. Power rule on this guy, that's going to be 3 times x to the negative 2. Constant multiple times a function. We know that multiple just hangs out, and we proved today that the derivative of sine of x is the cosine of x. And we also proved today that the derivative of the square root of x is 1 over 2 root x. So we have negative 2 over 2 root x. 2's cancel. And we now have a whole bank of tools, a whole bank of machines that tells us the slope of any function. Get a lot of practice with this. Take the homework seriously, and rest in the fact that all of this is proven, and rest in the fact of how powerful this new tool of the derivative is.